So in today's lecture, we're going to provide a formula, a general method of solving the first order ODE. So make sure to write it down in this specific form, the so-called standard form. With all the methods we're going to learn in this class, you need to make sure your equation is in the proper form, because when we develop a formula for any equation, we must agree on how to write the equation to begin with. So any first order ODE can be written in this form. You can get y prime by itself, and then if you combine the terms this way, you'll have a function of t times y, and then b of t, another function of t, maybe on the right hand side. So any first order ODE can be written in this form. If it's not in this form, then you have to bring it in that form by making some algebra manipulations, and you'll see later how that works. So the formula to solve this actually is very straightforward. It just involves two integrals, and I should point out again that the formula, you don't have to memorize it. It's provided in the formula sheet. But I want to take some time today to actually go over how that formula comes to be. Occasionally in this class I'm going to provide proofs of some formulas, if they're not too long, just to see where they come from. Now the proofs don't have to be memorized, but I think it's useful to think about a little bit what's behind each formula and how ends up being the way it is, even though the proof itself, you don't have to use it. So the main idea actually in solving the first order ODE is to speculate, is to take advantage of the fact that these two terms kind of indicate that you may be able to use a product rule in reverse for the derivative. You don't have to write this down, but remember that when you differentiate the product of two functions, as you know from calculus 1, this is the product rule. So the fact that in this summation I have both y and y prime indicates that maybe with some little algebra trick I may actually produce a product rule which will allow me, hopefully, right, to write this summation into a single derivative. If I can bring everything inside the derivative like this, then I can eliminate the derivative by integrating both sides. So you can achieve this by multiplying both sides by the exponential e to the power the antiderivative of a of t dt. So if you multiply both sides by this exponential, you will see, maybe that's not obvious to see in the beginning, but if you pay attention, you will see that on the left side you end up with a product rule. So let's actually prove that this is what happens here. So when I multiply these both sides, I have on the left side, let's see, y prime plus y prime times e to the power, it's a bit messy here, just a second. So y prime times e to the power integral of a of t dt, and then plus y, I'm going to rearrange the factors a little bit here, times e to the power the integral of a of t dt times a of t, and on the right hand side, of course, b of t e to the power integral of a of t dt. So here you have a product rule, if you look carefully, because this is y prime, this is the exponential, and this is just y, but this quantity here is nothing but the derivative of e to the integral of a of t dt. Okay, so pause for a moment to think about a little bit. How do I actually differentiate an exponential? So e to any function, if I differentiate it, right, it's the same thing, right, times via the chain rule the derivative of this exponent. But what's the derivative of an antiderivative? That's just a of t. So the derivative of the integral is nothing but a of t. So this basically fits the product rule. Y prime times this plus y times the derivative of that exponential. All right, so again, pause for a moment to think about for a little while and notice that this is just the product rule. So that allows me basically to combine the left side into the derivative of a product. And on the right hand side, b of t e to the integral of a of t dt. This is the so-called method of integrating factor, right? I mean, you basically multiply by a factor, that convenient factor which allows you to integrate. There is another method in the book called variation of parameters for the same formula. I won't cover that method. So even though the homework may say use both methods to solve these ODEs, just use the formula provided in the formula sheet coming from this integrating factor. So the next thing is to eliminate the derivative by essentially taking the integral, another integral on both sides. Right? So when I take the integral of this big derivative, I'm going to be left with y e to the integral of a of t dt. And on the right hand side is an integral of another integral, right? So an integral of b of t e to the integral of a of t dt and dt. It looks a little bit messy here, but we can write it in a much nicer formula pretty soon. And of course, don't forget the concept of integration, right? So when you're done with the big integral that eliminates the derivative, don't forget to add that concept of integration on the right hand side. So remember, the goal is to get y by itself, and we could do this if I multiply by or divide by this exponential, which is the same as multiplying by e to the minus integral of a of t dt. Right? So this is simply to move this exponential to the right hand side. So basically the formula for the solution then, y of t is e to the minus integral of a of t dt times quantity c plus the integral of b of t e to the integral of a of t dt and dt here. This doesn't look too pretty. You can use it right away, but what I like to do is to actually make some notations for these integrals. Because again, remember, to achieve this solution, right, to achieve this formula in practical applications basically means you have to find two integrals. But you need to find them in a specific order. So notice, I need to find the integral of a of t first before I can find the second integral here, b of t e to the integral of a of t dt. So then let's just make some notations. Suppose I1 is the integral of a of t dt. You do that first, and then of course I2, it's the integral of b of t e to the I1 dt. So once you produce these two integrals in this order, then your solution y is e to the minus I1 c plus I2. So like that, or you'll see in some cases you could simplify it better if you distribute this e to the minus I1. So this can be written as c e to the minus I1 plus e to the minus I1 times I2. Another reason why you may want to write it this way is because you will see that this ends up being the homogeneous part of the solution, and this ends up being the particular part of the solution. Remember, the most important theorem for linear systems we talked about last time: any linear ODE is made of two parts, the general solution of the homogeneous part, the particular solution of the original problem. So often it's better to write it this way because you will see the structure of the solution clearly, by identifying immediately what's the homogeneous part. The reason why the formula is written this way is because of the way it's produced, right? And sometimes if you have to memorize it, it's just easier to memorize it with e to the minus I1 on the outside. So let's go over a couple of examples. In the second part of the lecture, I'll just go over extra examples and some remarks. So for now, let's put one example here. So let's say y prime minus y equals 3 to the t. So remember, the first thing to do, make sure your equation is in the proper form or the standard form, y prime by itself, and then something times y, b of t on the right hand side. Because it's important to identify correctly what a of t is or what b of t is. So in this case, a of t is minus 1, b of t is 3 to the t. And then you proceed with the formula. I1 is the integral of minus 1 dt, which is minus t in this case. I2 is the integral of b of t e to the minus I1, which in my case is the integral of 3 to the t times e to the minus I1. That's no, e to the I1, I'm sorry. So integral of b of t e to the I1, and in my case that's 3 to the t e to the minus t dt. Make sure you do all the simplifications necessary here. So e to the t to the minus t becomes 1, so that's just e to the 0, and that means e to the 3 dt. So I2 becomes then 3t. Alright, and finally the full solution is e to the minus I1. There's a minus in the formula there, right? So minus I1, that's e to the minus minus t. Quantity c plus I2, which is 3t. So this is e to the t quantity c plus 3t, or if you split it, that's c to the t plus 3t e to the 3 e to the t. One last remark I want to make here. Notice you should recognize immediately that c to the t is the homogeneous part of the solution. The reason why you should recognize this quickly is because the homogeneous part of the equation is an exponential one. You guys remember the one equation I asked you to remember or to memorize. So if I drop the 3 to the t, which is the non-homogeneous term, and you make 0 on the right side, this becomes y prime equals y, whose solution is c to the t. Now, of course, the particular solution won't be easy to guess, which is the reason why it's important to have this general formula of solving first order ODEs. So with that being said, in the second part, as I mentioned already, I'm going to go over 2 more examples for this topic.